Welcome to the answer video of the copper tubing question. My name is Sharon and I will explain you how you could solve the copper tubing exercise. In the situation described by the exercise, heat is produced in a tube. And we would like to investigate in this question the temperature profile in the tube wall due to this heat production. For a first rough estimation, we assume the tube to be a flat plate, which you can see in the sketch. The length of the tube is 0.5 meters, so half of the tube is 0.25 meters. The first question was, which balance do you use to be able to calculate the temperature in the middle of the tube? Of course, temperature is all about energy, so you only need the energy balance. And the second question was, which law will you use to describe the flux in the part dx if you set up a balance over a small part dx of the tube? And that is of course Fourier's law, because that has to do with the temperature change. In this situation we assume the middle temperature of the tube to be 20 degrees Celsius. If you now set up the energy balance over a small part of the tube dx, you can investigate the temperature profile in the tube from x is 0 to x is L, so the length. Furthermore, you get some information. You need to calculate the temperature at a specific point, namely at x is 0.10 meters, so which is around here. During this question you have to keep in mind that the produced heat is exclusively transported through the copper tube wall to the ends of the tube, and that the middle of the tube is 20 degrees Celsius because of this heat production. So we now assume for this question that the heat flux is constant. This is very important for the rest of the question, so remember this. And furthermore, you get a value for the heat transfer coefficients of copper, 400 watts per meter per degrees Celsius. So now you can set up the energy balance. The energy balance has to be set up over the small part dx where the heat is transferring through the surface and heat is produced, which gives the following equation. The energy balance equals 0 because the situation is stationary. This means that the heat flux in and the heat flux out are the same. So the heat flux overall is constant, which was already given. Filling in the equation stated by Fourier's law for the heat flux gives this equation, which is constant, so we call it C1. Now we have to use the boundary conditions. The boundary conditions are that if x is 0, the temperature is 20 degrees Celsius, and at x is L, the temperature is 0 degrees Celsius because it's on the edge of the tube. If we now solve the equation, we get this. And if you integrate this, you will find this equation. Again, using the boundary conditions results in C2 is 20. Filling in the equation for x is L with the value for C2 results in this equation. And if we solve this, we find a value for C1. If you fill in this constant, we get an overall equation for the temperature. And if you now fill in the equation for x is 0.10 meters, then you will find an answer of 12 degrees Celsius. The third question asks you to draw the temperature profile for the copper tube in the sketch by using the temperature profile you had to set up in the previous question. So from the equation you see that it's a linear equation, and you know that at x is 0 the temperature is 20 degrees Celsius and for x is L the temperature is 0 degrees Celsius. So because it's a linear equation, you now only have to draw the temperature profile, which is a linear line. So this is how the temperature profile looks like in the copper tubing, if you assume it to be a flat plate. But of course it is not a flat plate. To get a more realistic temperature profile, we are going to approach the tube as a cylinder. The length of the tube is still 0.5 meters and the outer diameter 2.5 centimeters, and the wall thickness of the tube is 2 millimeters. The heat production is 20 watt in the whole tube wall, and to help you solve this problem, you see the sketch of the situation in the left corner. The first question for the cylinder situation was to finish the sketch with all the necessary information. You see now the answer in the left corner. And the second question was to set up again an energy balance over a small part of the tube, dx, and to solve it and calculate the temperature in degrees Celsius in the middle of the tube. I've already written down the heat transfer coefficient of copper. The energy balance over the small part is the heat flux in minus the heat flux out plus the production in the whole tube. So Q divided by the length of the tube, which is 2 times L. Because then you have the heat production per meter, and that is what you want because you have to multiply it by dx, which is the small part you are observing. Of course, the energy balance equals 0 because the situation is stationary. We can now rewrite the heat fluxes with Fourier's law. A is the surface where the heat flux is transported to, and that is not a flat plate, but it's now a tube. So we need to observe this surface of the tube, because there is the heat flowing through. And we know that the whole tube has a diameter of d and the layer thickness is delta. So the surface is described as follows, and if you write this out you will find this equation. And because squared the layer thickness is much lower than the layer thickness times the diameter, we can neglect this term and we only use P thickness times the diameter. Substituting this into the equation results in this. We can solve the equation by using the boundary conditions, and the boundary conditions are, if you think about it, very logical because the temperature difference at point X is 0 in the sketch is 0, because the production in the middle is exactly the same. The heat will only transfer from the middle of the tube to the ends of the tube and not transferring to the middle of the tube, so it has to be 0 there. And we know that at the ends the temperature needs to be 0. If we now solve the equation, we will find an equation with a first constant. But if we use the first boundary condition and we fill in x is 0 and the temperature difference over the x is 0, then we will find C1 is 0. If we further integrate the equation, you will find this equation with one more constant. And if you use the second boundary condition, then we found for the second constant that it needs to be this. If you now fill in the constant in the equation, we will find the temperature equation dependent on the position x. If we want to know the temperature in the middle of the tube, we only have to fill in the equation for x is 0 and we will find a temperature of 90.9 degrees Celsius. So our first rough estimation by approaching the tube as a flat plate was not that far from the real temperature in the middle of the tube. The sixth question asks you to calculate the temperature at a specific point, namely at x is 0.10 meters. And then you will find a temperature of 16.7 degrees Celsius. And if you do the same for x is minus 0.10 meters, you will also find a temperature of 16.7 degrees Celsius, because of course the tube is symmetric. The last question asks you to draw the temperature curve of the symmetric tube in the graph below. Well, the temperature profile is as follows. You look to the equation and you see that it's a quadratic equation, so it's not non-linear. And you know that at x is 0 the temperature is 90.9 degrees Celsius, and at x is 0.10 and x is minus 0.10 the temperatures are 60.7 degrees Celsius. So we need it to be a parabolic equation. So it needs to be a parabolic graph. And this is how it looks like. Thank you for watching this video and good luck with the rest of the exercises. And if you have more questions, you can always contact us or the other students via the forum.